A group of us have been in a study for a while looking at providing power for climbers on the space elevator, and I've been looking at solar power, and in particular looking at the use of perovskite as the main material. This is promising because it works best when it's extremely thin and therefore not very heavy, which is quite important for space elevator climbers because they do actually have to work in full gravity rather than microgravity. It's a promising material because other components of solar cells could be assembled on the moon without having to be transported from Earth, for example. There have also been tests in space of perovskite, and they have shown to stand up very well to the harsh environment of space. In fact, better than they do on Earth, because on Earth, perovskite cells are susceptible to moisture, and so precautions have to be taken on Earth. So with that promise, let's have a look at structure. The idea is you have a cathode and an anode. The perovskite's in the middle in that sandwich, the p-type contact, also known as the hole transporting layer, and the n-type contact or electron transporting layer. And solar radiation comes in, or some other radiation, and the electrons go one way and the holes go the other way. So you get a potential difference, and that creates a circuit. It powers a circuit. There's more than one structure for a perovskite cell. Here is one with silver at the top, and then a chemical called PCBM. I won't try and read out the full name. The perovskite layer itself, and there are several forms of perovskite. It's a crystal. For example, there are some forms that do not use lead, but the more efficient ones do use lead. PEDOT, PEDOT, and then indium tin oxide in that case. In another design, they use gold at the top as the conductor, and then the electron transporting layer is that. The perovskite's in the middle again, and you get carbon-loaded titanium dioxide, and then a substrate. So with those two ideas in mind, let's have a look at some facts about them. Typical cells are less than 1 micron thick. 1 micron is 40 millionths of an inch. The density of perovskite is 4 times water, so it's not particularly light, but the point is it's very, very thin and therefore doesn't weigh much. We can expect to get 400 watts per square meter from the solar radiation of 1361. And in order to get a useful 4 megawatts mechanical power, we need to generate, I think, about 5 megawatts. At least I think that's a reasonable working assumption. To generate 5 megawatts, you need 12,500 square meter. That would be a radius of 63 meters or diameter of 400 feet. So not small. That would be enough for a 20-ton climber. A bigger one would power a bigger climber, of course. So here's a mass estimate and summary of thickness, or should I say thinness. The conductive layer, which could be silver, which actually is the heaviest component by density here. Then the p-type contact, the hole transporting layer, the perovskite, the n-type contact, electron transporting layer, the conducting substrate, and then in addition, I'll come to the mechanical support for it a little later. So a flat sheet of 12,500 square meters has a mass of 37.5 kilograms, but in my opinion, a sphere is a more viable option, even though, of course, it's 4 times the area and therefore will have 4 times the mass. So that leads on to questions about the mechanical shape. A flat membrane suspended inside a ring is one idea. The membrane then supports the sheet of perovskite cells, and that needs a tilting mechanism. And then the alternative is a spherical shape. One idea is to form it by effectively 2 dome umbrellas, one inverted, and the other formed of a membrane supported by an array of 24 rods compressed by a tension mechanism. That's, in my opinion, the only one of these ideas that's viable. In any case, we will need some other way of getting power to the climber in the atmosphere, maybe an extension cable or maybe some form of winching, because these structures are far too large to be deployed in the atmosphere. So here's an illustration of a ring supporting a sheet. But if you do the calculations using Euler's formula, you find that to prevent buckling, the ring needs a mass over 100 tons. So that is clearly not on. Analysis of similar structures is in this particular conference reference of 5 years ago. Dome umbrellas are interesting. They're extremely light considering how big they are and what they do. But when you look at the structure, you know, a strut under compression pushes the outside rod away from the center. Those struts actually turn out to be quite heavy. So in an umbrella with 24 struts, that's 31 tons. Since you need 2 umbrellas opposing each other, 62 tons is not viable either. So that brings me to the wireframe membrane. And so the idea is here, rather like an umbrella, you have a membrane which is under tension and holds, helps to keep the rods in place, because to begin with, the structure has to be folded up and then it has to be deployed outside the atmosphere. So a calculation shows a membrane mass of 150 kilograms to support the perovskite cells, and that will be outside the sphere that's composed of these 24 rods. So that's looking a bit more hopeful. So in the atmosphere, it has to be folded up. And then when we get above the atmosphere, we need to deploy. And as I mentioned, another power method is needed in the atmosphere. So when we're above the atmosphere, then we can start to deploy. And the idea is that inner tethers pull the top and the bottom together to force the rods to bow outwards. And there will also be spacer plates in there to push them, to get them started. Once they're started, then the pulling force should be sufficient. I did, in fact, buy some rods of carbon fiber reinforced polymer, and they are stiff but bendable to this sort of radius of curvature without a tremendous amount of force. I mean, I can bend them with my bare hands. So I wanted to have some real ones just to get a feel for what happens. So then as we go, as I mentioned, the spacer is pulled down to help push the rods apart while the bottom is pulled up, and there's a similar arrangement at the top end. And so you keep going there, you pull and you squeeze, and in the end, you get these rods in the right place. Getting the shape governed by the shape of the membrane, but the rods will naturally form into an approximate semicircle anyway. So there's what the bottom of it looks like, with the spacer pushed down and the underneath bracket pushing it up. So the carbon fiber reinforced polymer rods, a 3 millimeter radius is sufficient. Length, since it's pi r, and I said the radius was 63, the length will be 198 meters. That's the mass density, and so 24 rods comes to 216 kilograms, which is reasonable. And each rod can take a maximum compressive force of 16 kilonewtons, which is about 1.5 tons force per rod. So, you know, capacity is there, it looks hopeful. Now, one issue that arises, however, is what to do about the way the sun moves, because there's more required than just the solar cells. We need to consider how we track the sun. Now, for the perovskite cells, we don't have to move them for the sun. They're light enough that we can afford the redundancy of covering the whole sphere with perovskite cells. That's 4 times the the area of perovskite that we would need if we had a flat membrane. But this shape, this solves that problem, and they're on the outside of the cells. The power conversion, though, we need to convert from 100 volts to 800 volts. 100 volts is about the limit generally agreed in practitioners of space-powered solar cells, that beyond that you tend to get flashover and sparking. So and 800 volts, of course, is far more efficient for transmitting power from the solar cells to the climber, bearing in mind that it depending on the time of day, it can be quite a long way. It can be more than 100 meters, and so the efficiency of that is important. If we got it to 1600 volts, it would be even more efficient for conducting, but a somewhat heavier power converter. So the state of the art in power conversion is about 20 kilowatts per kilogram. So for 5 megawatts, that comes to 250 kilograms. But this design has to track the sun. If we had redundancy and there was a power conversion for the whole of the sphere, its mass would be 1 ton, which is not at all appealing. So here's an illustration. There's a 3D model of you see the climber at the top. You see the rods in green. You can see the power converters, and the idea is that they will travel inside the sphere made of the rods. Now you can see little blue dots along there. They indicate where, this is obviously not to scale, but they indicate where the motors would need to be placed in order to move the power converters. At a very low speed, they only have to go round once every 24 hours. It's the same way as a clock, or in fact, half the speed of a normal clock. And so they don't actually have to be particularly powerful motors. They can be quite small. There are obviously some details to be worked out here, but the theory is that it should be possible to track the sun. You can see the tether, and the perovskite cells reside on the membrane all over the sphere on the outside. The power converters are on the inside. So this is what it looks like at 6 a.m. The sun coming from the east, and then this is 9 a.m. You've already seen noon. This is 3 p.m. This is 6 p.m. And we may need to go to 9 p.m. when we get higher up, when we get more sunshine. We may also want to have during the night the possibility of receiving laser power from Earth, but it would be a relatively broad beam compared with the narrow beam laser power that would otherwise be desirable. So it's possible also to have it round at the thing at the bottom, the power converter at the bottom. So that would give us a way to really get power for the whole 24 hours if we wish to do that. A hybrid system of solar power and laser is a possibility. So here's a provisional mass budget. There'll probably be other items to add into here. The perovskite cells, 150 kilograms, the membrane that supports them under tension, the same again. The rods, 215. Power converter, 250. 240 motors needed, but very small motors to move and align the power converter with the position of the sun. And the conductors still come at about 100 kilograms from the cells, from the power converter up to the climber. That's allowing a 200 kilowatt loss. If you allow a bigger loss, then you can make do with lighter conductors. So that there's a trade-off there as well.
1 minute, John.
Yes. Okay. I will show you the equations just to show that the equation calculations have been done. I'm not going to talk through these. I put them up as an exhibit just to reassure you that it is there and it will be published in due course. So in conclusion, for a 20-ton climber, 126-meter sphere is needed. For a 60-ton climber, it would be that size. There are still some detailed calculations needed. The balance of the tension in the membrane when we move the power converter around. power and forces involved in initial deployment of rods, unfolding the power converters during deployment, not trivial, needs to be worked on more. So in conclusion, using solar power for a climber is feasible, but not particularly straightforward.
I have a question. This is Jim Dempsey. Is the perovskite film or the self film flexible enough to be folded?
Yeah, the individual cells can certainly, well, yeah, I mean, I showed just a surface, but the surface consists of many cells, in fact, typically a few centimeters long by a couple of centimeters wide and very, very thin, as I indicated. So folding those is, I don't think, going to be a problem. I'm more concerned about the power converter, but I think there are ways of doing that as well.
And what about an inflatable structure as opposed to using the rigid rods?
I looked at an inflatable structure, but the weight for this volume, the weight of helium is actually higher than these other solutions.
Why does it have to be helium? If the solar cells are above atmosphere, you could use any available gas.
Well, hydrogen is the lightest, and that's half the mass of helium. But
Yeah.
even then, I did the calculation. I don't recall the numbers, but they were pretty big.
Okay, thank you.
Maybe there is a way with very, very low pressure. I'm not sure. It would be interesting if you've done some work on.
Well, I'm thinking of Project Echo. You know how they did that. You know, that inflatable mylar sphere that they had back in the 60s and that.
Yeah.
Larry?
John, you talked about moving the power converters around, and the question that immediately comes to mind is, how do they interface with the perovskite?
I envisage a set of contacts or hooks that they would engage with on each of those 24 rods.
And that collects the current?
That's the idea. Yes, needs more detailed work, but that's my thought.
Steve?
Hi, John. I really like the concept that you have here, and I'm sure it's at the beginning stages, but a couple of things I think you need to consider going forward that'll impact your weight calculations is you got a concern about tether rub. When it's folded up, you got to make sure it doesn't rub up against the tether. So there's going to be something there. In addition, I've been looking at some emergency operational conditions, so you have to consider deceleration and acceleration and the effect it'll have on your structure under various G loadings. So, you know, there are some dynamics. I'm sure you're at the beginning stage, but just for future.
I think to tether rub it will be an issue. I mean, this work with a bit more detail will go into the study report, but the tether rub, the real issue when we're traveling at 200 kilometers per hour or faster. And that has to be dealt with. We have to make sure there's enough space.
Yeah, just for the future. So.
Yeah. Okay, Blaise?
I was curious if you considered using a cylinder instead of a sphere, since the sun will be, going essentially in a circle around the climber.
Yeah, I looked at that. So I didn't show it as an option, but it is one. The rigidity. The thing is, your cylinder will be horizontal, and it's not clear how you make that work. It will tend to sag in the middle, and it's also not clear how you deploy it either. But if you can see a way to make it work, that would be interesting.